What we're going to be talking about now is the next topic that's considered truss analysis, even though it's not necessarily what we often think about as truss analysis. But it's going to be we're going to be talking more about frames and how frames are evaluated. What you see here is sort of a model of a standard wood framed house, and the problem is that a lot of people don't think about is when a house like this is built, there's an inherent instability in the design of a house because of the way the walls are framed. You can see here that we have a truss up at the top of the roof because it's one big triangle, but the walls aren't. The walls are not trusses at all. They're just made up of a bunch of different rectangles, so that when a lateral force is placed on the structure, such as wind or something, the whole house deforms like this. And this creates quite a bit of a problem because this house is unstable. And this motion here, called racking, that can cause quite a few problems in the house. It cracks the windows and the doors. The drywall on the inside. There's a bunch of cracks in it. Not to mention just overall structural failure of the building. But there's a lot of ripple effects that happen when a house isn't properly braced against lateral loads. Now here in Florida, one of our biggest concerns is wind. In other locations like California and places that have hurricanes, theirs might not be wind. It might be seismic activity where the ground underneath the building is moving. And if that's the case, if you move the ground, then the same phenomenon occurs. When the ground moves, the inertia, the mass of the house and its own inertia keeps part of that house not moving while the ground is moving. And so you'll get a response like this where the ground will move and then the house will, or the structure will, kind of spring back as the elasticity of the materials involved kind of bring that structure back to true or something close to it. In other cases, there's not enough inherent flexibility or strength in the structure, and when the bottom slides, the rest falls and you have catastrophic structural failure. And that's something we want to resist, and the easiest way to do it, or the most straightforward way to do it, is by means of diagonal bracing. So now that I have this piece of diagonal bracing, what this does is when I apply a lateral load, such as a wind load or something, what happens is now there's a stiffness to this, because now I have, if you look at the top of the wall and the side of the wall, it's bounded by this diagonal brace, which is just one of these little pieces of cardboard that I make that use as my tension indicators. And so when the wind blows from the left-hand side to the right-hand side, and it pushes against this house, now that diagonal bracing is there to keep that house true and the walls square and everything. When we switch the direction of the wind this way, you can see the house still is able to move, because now that diagonal member is in compression when we reverse the load. So now we have two diagonal members, and you can see when the house is being pushed from the left-hand side, it resists it because this diagonal member right here is in tension. When the member is pushed from this side, from the right-hand side, pushed towards the left, you can see the house still remains solid because now this diagonal member is in tension. So depending on which side the force is coming from, one of these diagonal members will be in tension, the other one, well, mathematically it would be in compression, but a cable or these little cardstock tension indicators that I made, they don't have any resistance to compression. So these would just be taken out of consideration when I have a force that puts that member in compression. Okay. Now, in a in a seismic scenario, the same phenomenon occurs. When the ground shakes and it moves towards the right, the mass of the house, the inertia of the house, forces it to the left. So as the base moves to the right, the top doesn't want to move, and so there's a lateral force acting upon the house opposite the direction that the ground is moving. And so if you don't have that tension member in, the house collapses to the left, and vice versa when you reverse the direction of the forces. Okay, so that's the system we're going to be working with. What I want to do is start to analyze this. We're going to simplify this and analyze it and look at some of the ripple effects of changing the layout of this setup. Okay, so we're going to start working on that in the next couple examples.